Thank you guys all for coming out tonight to talk with me about immunology, one of my favorite topics to talk about. And so tonight I want it to be kind of just a very kind of informal seminar, and I hope to answer some of your questions. And even more importantly, I want you guys to start asking questions and get to thinking about immunology a little bit more. So before we get into it, I want to tell you just a little bit more about myself. I grew up in Taos. And I went to school at New Mexico State University. I got my bachelor's degree in microbiology. And then I went to University of Arizona, where I got my PhD in immunology. And so it's been a great kind of journey, and I've also taken a lot of time to work with the school systems and try to do some science outreach activities that has been really fulfilling as well. And so I like talking to you guys about that type of thing. And I also worked a lot on a virus, which probably most of you are infected with, not to scare you. But that's always a good icebreaker because it's a virus called human cytomegalovirus. And we can talk about it more later with respect to the immune system. But again, it's something that is very common. It's one of the herpes viruses. Once you get them for life, so that's another thing too. And a lot of that has to do with the interplay with the immune system, which we'll talk about. Okay? All right, thanks again for coming. And like I said, I want this to be fairly informal. So my first question to you is, what do you know about immunology? Tell me. Yes.
The study of the immune system?
Yes, the study of the immune system. Good job. Okay, you guys got to know more than that. Give me some key words. Viruses, bacteria, yeah. Infection. White blood cells, good. Lymphocytes. Erythrocytes, yep. Monocytes. Yeah, so good. We're going to go over a lot of those cell types. Yeah, definitely. Have you guys heard of immunization? Okay, who here has been immunized? Probably most of you. In fact, all of you, as far as I can tell. So that's another thing that we're going to touch on tonight as well. Anything else? What have you heard about the immune system? Is it good to have it? One of those? Yes. Yeah? Yes.
It helps you fight germs.
Yes.
Bacteria.
Yes, exactly. It helps you fight germs and bacteria and all those viruses. And it's what keeps us healthy from some of those germs and bacteria that can actually harm us. And so we'll be able to explore some of that and see how that happens. All right, any other questions or terms before we get started? Okay. All right. So, like I said, we're going to touch on some of the cells, and we mentioned that a little bit. We're also going to talk about vaccination and just a little bit of the history of immunology, because yes, we can hear about it today, but where did this come from, and why do we study this defense system that is inside of our bodies? And we'll also talk about some of the immunology-associated health issues with regards to cancer, organ transplantation, autoimmunity, immunization, and immune deficiency. And so the title of our talk was Ready, Set, Attack. And so I want this presentation to be kind of along those lines as well. I really want us to get ready and see where immunology came from initially, and then I want us to get set with knowing some of the groundwork, baseline information that you need to essentially attack these big questions at the bottom. So that's the goal for this evening. And so in the beginning, now this was a very, very long time ago. All right, this is approximately 400 BC, 500 AD. there were some initial observations. And like I said, these were people who they didn't have the quality of life that we have now, right? They don't have their iPhone, they don't have their laptop, they don't have a lot of these kind of niceties. But instead, a lot of times they were fighting infection and epidemics of the plague, epidemics of other diseases. And people were dying left and right. And people wanted to understand why that was happening and if there was anything they can do about it. And so these were some of the observations some people kind of took note of. And that the same man was never attacked twice, never fatally. So if somebody got sick, and they recovered from that sickness, well then if they were, if their sister got really, 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 really sick, they could be close to their sister and not have that disease spread to them that second time. So these were some observations. Again, those who recovered were not liable to a second attack, and those who recovered were used to tend to the sick. So they kind of started using this. They're like, okay, you seem to have had this disease already, so why don't you go help everybody else, since we know from our other observations that you're not going to get sick. So again, this was way back in the day. People didn't necessarily quantitate these effects at that time, but what it did was it gave people the promise of protection. And this is kind of the theme that jump-started everything afterwards, was that there must be some reason why people don't get sick the second time. And so that was what people back in the day wanted to understand. And then there was smallpox. I know this is kind of a disturbing picture, but this is what our ancestors had to deal with. And this was everywhere in Europe, which there weren't very many people in Europe. But 400,000 people died every single year because of smallpox, because of this disease that causes these lesions all over the body. These lesions can leave disfiguring scars, and also, even if the person recovered, there's a chance that that person would go blind because of this disease. And so it was a really big problem, especially because nearly 80% of the children who contracted the smallpox disease ended up dying from it. So can you imagine living in that world? We are so fortunate today because of all those vaccinations you got as a kid, right? They're protecting you from things like this. And so, again, this was the challenge. And this was a different type of world that these people were living in. But you can imagine, if somebody of your family got this disease, you wanted to do something about it. And given those initial observations from before, we knew something about it, but we didn't know a lot about it. And so that was the challenge. And just a small note here on smallpox. Again, this virus was very influential in our history. You can think of it as the very first bioterrorism agent, because settlers were able to, they knew people who had not been exposed to this virus would get really, really sick. And so they would actually contaminate blankets and give them to some of the Native Americans who had no immunity to this virus. And then you can imagine if they were then to engage in war, well, it's really hard to fight a war if you're not feeling very well. So again, immunology, virology, all of these things have actually shaped our history in quite a few ways. Okay, so just a few more things about smallpox. Now, a lot of time has gone by, and we still don't have any answers on smallpox. Again, the initial observation that people who lived through initial exposure to smallpox did not contract the disease again. This suggested that it may be possible to have some protection against the disease. And some of these early philosophers were trying to do some experiments to actually see if this could happen, if you could get protection. And the idea was that it might be possible to give a small dose, like a really tiny bit of that smallpox virus, and give it so that the people would kind of get maybe a fever, maybe a few of those pock lesions, but they wouldn't have an extreme disease. And therefore, they would be protected against a future exposure to smallpox. So that's the idea, right? And what does it take to get a new idea or kind of a new way of thinking started? Testing. Yeah, exactly. You want some hard numbers, right? Right, yeah, exactly. And we're going to get to that too. But even before that, what makes people start getting kind of riled up about something? Publicity. Yes. We all care about what Jennifer Lopez is doing, right? Or or maybe not. Or Michael Jackson, what happened? Celebrity endorsement. We kind of eat that stuff up a little bit, huh? All right, so the same thing went for immunology and this idea. It wasn't until Lady Mary Wortley Montagu suffered from this disease, and she was a beautiful woman, and she survived, which was great, but she had some scarring that didn't really go away, and she was disfigured from then on, and she was really upset about that. And she was kind of in the upper class and had some status within her town. And what she did is she ended up hearing about this kind of application to take a little bit of that smallpox and give it to somebody who's never been exposed. She actually did this with her children. And she did it in front of the royal court. And she says, I believe in this technique. Look, I will bring my children in, give them a little dose of the smallpox vaccine or virus into a little scratch on their skin, and they'll be protected. And they actually were. And this was something called inoculation or variolation. And it's that same thing. They had actually, okay, sorry, this is kind of gross. Okay, if you have a really bad pimple, right? Has a little pussy head to it. Okay, they would actually, same thing with the smallpox. They would pop one of those, get a needle, get some of that good stuff, and then inoculate it into a little scratch on a child's arm or something, to just get them a little bit exposed. It wasn't like that person was breathing all over them or like rubbing up all over them, right? So they didn't get the full virus, but they got just a little bit, just enough to do the trick. And like I said, the celebrity endorsement definitely did help. And then soon enough, all of the royal family, the upper class people were starting to do this on a regular basis. Now the problem is how do you measure like one pimple's worth of smallpox, right? How do you do that? So there needed to be a better way. And the problem with this method, although it did provide some protection, was that some people actually died too, because there was, again, the measuring equipment wasn't there, so on and so forth, and so it was still quite risky. Yeah?
They found part of the cure for smallpox, which was involved that made him immune to the type of chickenpox, which...
Yes, you are on the right track. Not chickenpox, but cowpox. Yeah, yeah. Yep, exactly. Good thinking. Yeah, exactly. So his name was Edward Jenner. And he was the first person to actually, he's considered the father of immunology because these people knew these ideas, but nobody actually counted. Nobody actually did the experiments, had the controls, really did the legwork to make sure that, okay, now we have hard numbers that support this claim. And he went a step further, and he noticed that milkmaids were less likely to contract smallpox. But they often did get cowpox. And so they'd get a few little lesions on their hands, like over here. But they wouldn't die from this disease. And again, these milkmaids were immune to smallpox. So he put 2 and 2 together, and he thought, okay, maybe it's a little bit safer to inoculate people with cowpox instead of actual smallpox from a puffy lesion, right? And that's what he actually did. He did the experiment. And again, yeah, I don't know. Children are protected today in today's experiments. And also prisoners. They took a cohort of prisoners and actually did the first few experiments with prisoners to see if they could give them cowpox and then expose them to the smallpox. And they all survived. And so the experiment worked. Like I said, there's some safety nets these days, which we can be thankful for. But again, the principle held true. And then this was termed vaccination. So you can think vaca, cow, vaccination. That's where it came from. Well, the Latin word for a cow is vaca as well. So, any questions? Ideas? Okay.
Sorry.
You good? Okay. Yes. So now everybody's on the right track. And we have vaccination. Now you can imagine there were some skeptics. And people didn't want to necessarily be injected with a cow virus. What's a cow virus going to do to a person? Ooh, right? Like this picture shows. If you get the vaccination, does that make you have like cow parts now? And cow heads coming out everywhere? Yeah, so it takes a while for these things to happen, but those experiments keep going on and on and on, and that's the scientific process. And eventually it is accepted. So where's smallpox today? It's gone. The world is free of smallpox. Pretty cool, huh? Yeah, so nobody has to worry about it. And this was because of worldwide vaccination efforts. So this was a huge problem that we do not have to worry about anymore because of vaccination. In May 8th, 1980, the World Health Assembly announced the world was free of smallpox and recommended that all countries cease vaccination. The world and all its people have won freedom from smallpox, which was the most devastating disease sweeping in epidemic form through many countries since earliest times, leaving death, blindness, and disfigurement in its wake. Yes?
Is there actually a smallpox episode in the 20th century?
Now, there was some smallpox. It was always kind of lingering because not everybody was vaccinated. But we haven't had the big outbreak like in the days past. There were some smaller outbreaks in other parts of the world, not necessarily the developed countries.
Is it
Yeah, it is possible for smallpox to evolve. Now that we've eliminated this disease, it gives it a lot less chance to do that evolving, because you need it to keep replicating in something to start changing. And since it's not replicating, it can't change very well. Yeah?
Is smallpox part of the battery of immunizations that babies receive now, or they don't have that?
I don't believe it is anymore, because it's not necessarily a problem. Now, smallpox is on the bioterrorism list. So there are a few select labs in the world that actually do have vials of this virus. And those people are still working on this virus and still trying to understand it, just in case it resurfaces, which could always happen. So, and like the childhood vaccinations that we all get as kids, there are other very devastating diseases, some things that can kill babies a lot of times. So we're protected thanks to immunology, and this is where immunology came from. So any other questions on this part? Okay. All right. So now let's jump into the immune system. So let's get set to learn a little bit more about the immune system. And again, I think you guys have kind of come across this, that the function is to protect the body from invading pathogens, viruses, bacteria, fungus, parasites, toxins even, and also cancer. And we'll touch on that a little bit in a bit. And there's a few immune organs that you should be aware of. One is the thymus, the bone marrow, spleen, lymph nodes. The thymus is my favorite. I did a lot of work on studying T-cell development, and those T-cells, you guys have heard of T-cells, right? Who's heard of T-cells? Yeah, okay. Yeah, okay, so they are educated in the thymus. So all of you school-aged children, young adults, teenagers, think of yourself as young T-cells in the thymus. You're learning what's right, what's wrong. You're getting some education about your environment. And that's exactly what the T-cells in the thymus are doing. Now, you only have a thymus through puberty. And after puberty, your thymus starts to shrink up. And you really don't produce very many T-cells after that. So what you made as a child stays with you for the rest of your life. And so those T-cells are pretty hardy. They went through the education process. They went through the system. They came out. So we got to work with them, right? So now the bone marrow is another immune organ. That's where a lot of your B cells do their education process, is in the bone marrow. And that's where all of the cells from your immune system are born, essentially. So if somebody gets a brand new bone marrow transplant, they're essentially getting a brand new immune system. Because, again, all those cells originated in the bone marrow. And there's some really key stem cells in your bone marrow that can make all the other cells within your immune system. Now, the spleen is where a lot of your B cells and your T cells start getting activated. This is a little bit later on in the immune process. And there's a lot of B cells in your spleen. And your lymph nodes are really where there's kind of like the outposts in your body. This is where your immune systems start congregating and saying, your immune cells congregate and say, okay, well, there's a problem over here. There's a virus over here, and we need to get rid of it. So that's where they kind of set up their headquarters and end up sending out the troops. Okay. Now this is important as well. So I keep saying the immune system kind of analogous to an army. And it really kind of holds true, and I'll use this throughout. And there's really two lines of defense. The primary innate defense system, and this is where the cells involved block those bacteria or those viruses. They actually eat them up, and they end up showing or presenting the parts of the bacteria, the viruses, out so that the cells from the secondary adaptive line of defense can actually really know what they're going after and go out and kill it. And consequently, these are called the special forces or the secondary adaptive immune response. And it's more specialized. And those that actually got selected, these are the troops that really did a good job. Well, some of those will actually get immortality almost, some of those cells. And they'll stay with you for your whole entire life. And once they're with you, if you happen to come in contact with that virus or that bacteria again, well then, they've already seen it and they know how to kill it. And so they do it directly. Cool. Any questions? All right, I'm going to stand over here for a minute. All right. Yeah?
So is the spleen necessary to survival?
No. You can't take out a spleen. It's not going to help your immune system at all. And you will become some sort of immunocompromised without a spleen. So if you can keep your spleen, keep it.
So is there supplements or is there treatment after a splenectomy that's necessary to survive?
I'm not sure exactly. I would think you'd probably be okay still. Because you still have your lymph nodes, you still have B cells that are going to be around in other parts of your body.
Resistance potential.
Right, yeah. So you should be okay, but you'd have to be more careful, definitely. Yeah.
So for children that are not immunized, there's a trend now.
Right.
Do they not have these educated T cells, or are they missing some?
That's a little bit different, but they do have T cells just like everybody else, and they function.
The ones, say for fighting chickenpox, if they're not immunized.
They will still have those T cells. The T cells will still be there. But what they are lacking is that memory for that second infection. So if they're never immunized to begin with, and you're 20 years old or whatever, and then you get chickenpox for the first time, it's a chance that that's going to be a really, 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 really bad infection. And, maybe not chickenpox, but some other virus that may actually kill you. So it doesn't have anything to really do with the T cell development. It's more on that memory after getting exposed that first time. You had a question?
I was wondering what the role of the appendix is in the immune system, if there's more information about that role.
Some people do say, yeah, the appendix is considered one of the immune organs as well. I kind of take that on the fence a little bit, and I don't really know offhand how important it is. But like I said, the majority of the T cells and B cells and the other cells don't really live there. So, yeah. All right. Okay, so let's talk about some of those cells, because we already talked a little bit about them, but I want you guys to get really acquainted with them, because like I said, they will come in handy when we actually try to tackle those big questions. And we'll go through each of these individually, so you don't have to write this whole chart down or anything. I know some of you are taking notes. Okay. All right, so where they are, these cells are located in the body. They're usually in the tissues, the blood, the lymph nodes, the bone marrow. These are kind of the areas that a lot of these cells live. And their function altogether is to inhibit infection of those bacteria, viruses, etc. And they have very specialized ways of communicating with each other, too. And like I said before, there's those two main arms of the immune system, the innate and the adaptive immune response. And this just kind of breaks it down according to cell as to which cell is involved in which part of the immune system. All right, so like I said, we'll go through these one by one. Okay, the monocytes, macrophages, and neutrophils. You guys said white blood cells was something, right? Okay, so these are, I mean, all the cells in your body are considered white blood cells because they're not red, right? But these are the major ones that are considered your white blood cells. If they're in your tissues or somewhere and there's a bunch of them, then you're considered to have an infection in that area. And it's these cells that start accumulating. And so they're in your peripheral tissues. Some of the neutrophils are even in your blood. And these are the guys that, I call them the triage nurses, kind of, because they're the first ones to kind of encounter those bacteria or those viruses. And what they do is they start eating them up and then show it to the cells of the adaptive immune system. And so I kind of diagrammed this here. Here's a monocyte, and these rectangles are, say, a bacteria. And the monocyte, once it senses that there's bacteria out there, it starts a process called differentiation, and it becomes a macrophage. And you can think of the macrophages as like macrophage is kind of a scary word, right? Like, who would want to come up across a macrophage in a dark alley? So these cells actually start eating the bacteria. They actually engulf the bacteria. They chew it up. They put a lot of enzymes in there, and they process it. And then they put out little pieces of that bacteria on proteins called MHC. And those MHCs are used to communicate with cells of the adaptive immune system, but also mostly that's the function. But those proteins are out, so like it's a sign saying, hey, okay, I just ate a bacteria. Something's wrong here, okay? And what these macrophages also do is they secrete cytokines. And cytokines you can kind of think of as hormones. Very quick acting, very small molecules. This is what starts your fever, or starts you getting that really kind of drained feeling. That's because of the cytokines. And the role of the cytokines is, again, to talk to your brain a little bit and say, okay, we have a big problem. Why don't you jack up the temperature, try to smoke these guys out, okay? And some of these cytokines, if they first encountered a virus or they encountered a bacteria, kind of the profile of these cytokines that are made after this macrophage talks to like a T cell or a B cell can tell your body, okay, we're dealing with a virus or we're dealing with a bacteria. So let's really focus our efforts in that area. Now, there's some smart bacteria and some smart viruses. And those, for example, some of those bacteria make themselves look like viruses to the immune system. So then the immune system starts going after a virus, but it's really a bacteria that's caused the problem. So you can see it's kind of a dynamic interplay. And then the neutrophils. So these cytokines are secreted. The neutrophils are kind of hanging out in the blood. And what happens is that those cytokines are released, and it makes those cells around the blood vessels a little leakier so that these neutrophils can get into the site of infection. And the neutrophils, again, start eating up the bacteria, eating it up. They produce a lot more of those cytokines. And that's the red, swelling, bumpy thing. If you have a really bad scrape or something and it's infected, and it's red, and it hurts, those are the cytokines and the neutrophils and everybody trying to get in on the action of killing these bugs. Okay? Questions?
So is this the stage where a resistant bacteria like MRSA, one of those, can happen? Is this the stage?
Yeah, it pretty much evades all the stages, but this is the first one. Yeah. The macrophages can ingest it, but it can replicate so fast, and other parts of the immune system can't inhibit that replication that it ends up not being killed. And then you have an infection that could kill you. Right. Exactly. Yeah.
So do herpes and AIDS, like, do they disguise themselves as something different?
Yeah, pretty much every bug has its own little toolkit as far as how it can evade the immune system. And those two viruses have a little bit different technique than at this stage. They are HIV and the herpes viruses. Yeah, so these viruses actually do a little different technique. They hide out in cells of the immune system. And if you kind of like, if you're hanging out on the other side, then it's hard to recognize if you're a good guy or a bad guy type of thing. So that's kind of more their mechanism. Good question. Anything else? Okay. So I have a fun fact for you. Okay. The neutrophils are the most numerous white blood cells in the circulation. There's a ton of them. And these are these guys. So like I said, it's not surprising that if you get a cut or something that as soon as 10 minutes later, it's red. Because you got a bunch of neutrophils hanging out ready to attack. Okay, so let's go into the dendritic cells. These are really cool cells. And they look like that, really. They have very long arms, and they're very good at eating those bacteria and viruses, too. They're very good at that. And they're really specialized. They're called professional antigen-presenting cells. And the antigen I'm talking about is the proteins from that bacteria that got chewed up, that are on the surface of the cell. So they eat that up, but these cells are so good that they don't just eat them up and hang out. They eat it up, and then they travel to the lymph node. And the lymph node is where the real party happens. The lymph node is where the dendritic cells, and they can secrete cytokines as well, but the dendritic cell comes in contact with the T cells, and there's two main subsets, the cytotoxic T cells and the helper T cells. And they communicate with, again, that protein MHC. And there's a couple different classes of MHC. But again, this is how they communicate. They touch each other and they're like, okay, you just came in contact with a bacteria. I have to do something about that if I'm the T cell. I need to do something about it, which is I'm going to start proliferating. If that contact is strong enough, the T cells can proliferate, and some of the T cells called the helper T cells then interact with the B cells, and the B cells, we'll get to them, are really good at secreting these things called antibodies. And they're proteins that are really good at neutralizing the bacteria or the virus. Okay, so dendritic cells, they're pretty cool. They're the communication bridge. So they are considered the specialists. All right. Okay, yeah. Fun fact. Sorry, almost forgot. Everybody feel your neck. Right there. You know when you go to the doctor's office, and the first thing they do is check your neck? They're looking at your lymph nodes. Anybody have big, knobby things? Yeah, they're kind of round, kind of oblong. if you're feeling pretty good right now, you probably won't feel them very well. Okay, but if they're really big and kind of hard, then you have an infection happening. Okay? Welcome to your lymph node. Okay. Okay, so that was mostly your innate immune response. So let's get into the specialized forces. Those are the T cells. And again, they originate in the thymus. They're in the blood. They're in the lymph nodes. And depending on the type of T cell, they can directly kill infected cells or talk again to the B cells and get them activated. And so here, the cytotoxic T cells, they're also called CD8 T cells because they have a protein called CD8 on their surface, which makes them look a little bit different than the other T cells. I consider these the snipers. So once they got activated in the lymph node, then they're like, okay, I know what I'm going after. They get into the blood, and they go right back to that site of infection, and they start killing. And they can kill directly. So how they kill, oh, you can't see it very well on here, but this T cell can actually punch holes in the infected cells. And this is mostly important for like a virus infection because the virus will first infect normal cells and kind of hang out in there as long as they can. But the T cells, again, can detect the infected cells, and then they punch holes. And once those holes are punched, the cell starts spreading out and leaking all its good stuff, and it's dead. Yeah?
Is there any proven approaches to building the immune system, to making it stronger?
Making it really strong? There's not really any great ones. You can make an immune response, say for like a vaccination. You can make that stronger by adding some like metals or other types of things to that prep. And so you make a really strong immune response. But that's not really your question. Your question is if I assume if you're feeling really tired, really drained, how do you kind of boost your immune system up? I'm not aware of any real great quick fixes, unfortunately. But nutrition's one, sleep's one, all of those things. As long as you're healthy, you're keeping your immune system healthy. Yeah. There's some things that are in the works, and everybody will tell you that they have the magic thing that will boost your immune system. And it may temporarily, but it's just kind of a automatic response. If you give your body something different, your immune system's going to be like, what is this? So it's going to have some sort of reaction, but it won't be that specialized reaction. Yeah?
How related are allergies to immune system?
They are.
I think so. I mean, it makes sense, but...
Yeah, so allergies are a function of your immune system as well. And what happens with allergies is it's kind of an over-response of your immune system to something innocuous. And through evolution, at one point or another, that was advantageous. So we still kind of have the remnants of that. And what it is that if you're in contact with ragweed or something like that, your immune system sees that as an invader. And some of those cells start secreting histamine. And the histamine is kind of something that will kind of start telling your brain and everything else, okay, get all your fluids out, water the eyes, Your nose starts running, you start making a lot of mucus, all that good stuff, to try to inhibit that invader. But it's really not an invader to us. So it gets a little bit confused. And in that sense, you go out and you buy an antihistamine. So you're actually buying a little immune suppressant to those cells that make the histamine. And to kind of, to kind of gum up that histamine so it's not saying, okay, create a lot of mucus, all that. Yeah. Great. So, okay, so we've got our T cells and 2 subsets. And again, these are the special forces. And once those holes are punched, the cell dies. And over here, our helper T cells actually talk to the B cells again with that MHC. And the B cells start making antibodies. And we'll get to that in just a second. But before that, fun fact, estimated 98% of all the immature T cells flunk out of thymic education school. Okay, so you guys are in school. I hope you all are getting very good grades. I'm going to sign something to give you credit in some class, right? So that should help. I don't want to see you guys become one of these, okay? They flunk out because in the thymus, if you can react with yourself as a T cell, you're out. Because if you have a T cell that exits the thymus and then starts thinking your kidney looks a little strange, well, you kind of need your kidney. So you want to get rid of those T cells at the very beginning. And a lot of those end up, dying. But on the other hand, you keep all the ones that don't recognize yourself. So that the hope is that they will recognize something else, a bacteria or a virus or proteins from that sense. Okay? All right. So let's get to the B cells. B cells are pretty cool. We're almost through the cells. I know there's a lot of cells, but they all have their cool things. They originate in the bone marrow. They're in the lymph nodes and in the spleen. They make these neutralizing antibodies. And here's a picture of an antibody that will inactivate the pathogen. So in this antibody, it reacts with antigen. And antigen kind of sounds like pathogen, right? A pathogen is like a bacteria or a virus. Once that pathogen is broken down into its protein components, those protein components are called antigens. And antibody can bind those antigens. And so if you have even a full bacteria, those antibodies, once you start making them from the B cells, are flowing through your blood, and they come in contact with that bacteria, and they neutralize it. So they bind to the whole bacteria so that the bacteria cannot infect your cells, cannot cause any problems to you because it's all full of these antibodies. And then you have other cells in your immune system that say, okay, this is a bacteria full of antibodies, let's eat it. So, yeah. That's fine, I like it.
What is the role of antibiotics, and is it true or false that antibiotics wreck your immune system?
Okay.
Natural immune system.
All right, the question is, how are antibiotics related to the immune system, and do they have an effect on your immune system? Right, okay, so antibiotics, your body necessarily doesn't really make antibiotics because it has these special cells to do all the really cool stuff. But antibiotics were originally isolated from fungus, and a natural predator of fungus is bacteria. And so the fungus wanted to not get infected by the bacteria. So it started making these chemicals, antibiotics, that were able to kill that bacteria. And so we've isolated that from organisms, or plants make them too. And then we're able to take a pill of that concentrated dose, and then that travels through our body. And if it comes in contact with bacteria, it will kill them. And one thing your doctor will say, okay, if you have an antibiotic be careful, it may kill the good bacteria too, and it does, because it's not really specific like that. It's not nearly as kind of specialized as this system is. And can they affect your immune system? Definitely. They kind of take some of the load off, right? There is a natural progression if you're infected with something that this immune system goes through, and it takes about a week, 2 weeks to do. Well, we're busy people. We need to have, a life. So we take an antibiotic, and it cuts down that time that this process takes. Now, this process still happens, but not quite to the level as before. And then on a separate note, which we'll get to a little bit later, the presence of a lot of antibiotics in the environment, in our everyday lives, well, that's killing a lot of the good bacteria. So then we're not really exposed to a lot of even the good bacteria or the bad bacteria, so our immune system ends up not knowing what to fight. Because if everything's clean all the time, well then your immune system's just kind of hanging out like, come on, give me something. And the problem is if you don't give it anything, it will start attacking yourself. And so allergies, but especially asthma, has been linked to kind of growing up in a very sterile environment and more a problem of the developed world compared to the developing world. Yeah, so we'll get back to some of that kind of real tie-ins a little more later. Yeah.
So asthma attacks the immune system, or how does that work?
Asthma is, well, one part of the asthma is a function of the immune system. Remember those neutrophils that start going to the side of infection or problem? Well, if you have an asthma attack, a lot of that's just inflammation, those cells getting in the airways and constricting it. So then you can't breathe. And so if we could eliminate a way for those cells not to be kind of triggered to go to that area or think that there's really a problem when there's really not a problem, then we can get rid of asthma. Yeah. Great. Yes. Okay.
What causes inflammation, or what does it do? Is it just to protect, or why do things come in place when your immune system is down?
Right. Okay. So the question is, what is inflammation, and what does it do? What's its function? Okay. So inflammation is one of those macrophages came in contact with something, and it started this chain reaction of secreting those cytokines and then recruiting the neutrophils all to that same area. So the combination of the neutrophils in there and the cytokines and all those extra cells in that space is inflammation. And the function of inflammation is if you have all those immune system cells in that space and all those kind of toxic cytokines, it's going to be kind of hard for a bacteria virus to live. And so it gets rid of it. Yeah. Great. Good questions, you guys. Yes? Why do you get asthma? So part of it's genetic, but part of it is also environmental, where you grew up. And that's some of the studies that have started as to people who are, again, kind of raised in more clean environments versus living on a farm growing up. The people in the cleaner environments tend to have more asthma than the ones living on the farm. So a lot of the mechanisms aren't known, but we do know some of those associations. And then it's a combination of the environment and the genetic factors. And all those kind of come together so that that person ends up having asthma.
What about the role of stress and the immune system? Stress.
Okay.
Immune system.
The role of stress in the immune system. So that's a great thing. Everybody's kind of stressed out, right, these days. So School can be stressful, right? Okay. Okay, so when you are stressed out, you tend to not get a lot of sleep. You also tend to make hydrocortisone. And hydrocortisone is called, another name for it is the stress hormone. So these stress hormones start building up in your body, and the mechanism of it eventually is if you're under a lot of stress, you can react quickly to something else and kind of get out of danger or something like that. But if you have a buildup of that hydrocortisone, it can actually decrease your immune system. It's another immune suppressant. And so if any of you have ever broken out in hives, and I have, from rosemary olive oil Triscuits. I'll never eat them again. They were so good. Okay, but I had to go to the doctor, and they gave me prednisone, or yeah, I think prednisone. They gave me some sort of steroid. And steroids are very similar to those stress hormones, and what it did was dampen my immune system so that I didn't make that kind of false reaction. And so it does. It decreases your immune system functioning and also the number of cells involved in those responses. Yeah. Okay. All right. Right. Yeah.
React to that even though you're in ready flight.
Right. Or that reaction may take longer than it would happen normally, which gives the bugs kind of an advantage.
Why would they give you a steroid to depress your immune system?
Because I was having hives, which is very similar to the allergies scenario, and so it was against rosemary olive oil Triscuits. They're not going to kill me. So it was an overreaction of my immune system, which has consequences of its own to me. So I didn't want that. So you can actually decrease your immune system if that happens.
And that's only temporary unless you have long-term use.
Right. Right, yeah. Some people, organ donors, organ recipients have to be on lifelong immunosuppressants. We'll get to that. Great, okay. All right, B cells. They're a fun fact. Antibodies can be generated to bind nearly any substance. Any substance, which is pretty amazing. So we use antibodies all the time in biotechnology. They're key reagents in the lab. You can put little fluorophores on the ends of them so they light up when you excite them with UV light. So you can see where something is inside of a cell. You can put enzymes on the end of them. You can also put toxins on the end of them. Some thought is that if we want a really directed response to something, let's make a bunch of antibodies against something. And then if we want to kill that, well, then we put a toxin with it, too. And it can go into your system and kill it. Yeah?
So that's how it realizes what's intact. Because it feels on the antigens that it goes after.
Right, right, exactly. And that's kind of this little mini evolution. So once if these antibodies can bind when the antibodies are on the surface of the B cell, then this B cell gets to live. And it makes a lot of itself. And then those antibodies are all generated against that one antigen because it's the same cell that cloned itself, essentially. And then even after that, the antibodies get stronger and stronger as time goes on. So it's really cool. It's pretty fascinating. All right. I'll go through this real quick because we'll touch on it again. But the immune cells and functions, these are the NK cells, natural killers cells. Okay. These are in the blood, periphery tissues. They measure the concentration of those MHC molecules. So if you have normal cells with a normal concentration, you're good. You get to live. If you have too few of those MHC molecules. A lot of times these cells are infected with a virus. One of the tools in the toolbox of a virus is to decrease these number of molecules, because these molecules communicate with the immune system. So if there's no molecule, you can't communicate. But NK cells will come along and measure that. And if there's too few, those cells will die. Also, if there's too many MHC molecules on the outside, this happens a lot of times in cancer. So if a cell is dividing really, really fast and things are kind of jumbled up inside the cell anyway, a lot of times this concentration gets off, and so the NK cells can recognize that, and then those cells die as well. So these are definitely the undercover spies of your immune system. And I said this already, the NK cells are especially good at killing virus-infected cells. Nice to have natural killers within you, all of you. Okay. Again, here's the cells. Summary of the immune system. You have the organs. You want a protection from pathogens. Two main components, the innate and adaptive immune response. The development of the immune system is key. And many important disease states rely on the status of the immune system, which we've been talking about a little bit. So I want to get to those. We've talked about cancer just briefly. Again, if we all have had cancer, every one of us, but at one point or another, our immune system came across that cancer cell and said, okay, you may still be self, you still may be my cell, but you look strange. There's something wrong because that concentration's off. And the immune system ends up killing those cells as well. So that's one of the problems of continued immune suppressant. You can imagine there's a possibility for cancer. Organ transplantation, this is huge. So again, your immune system knows whether it's from you or someone else. And someone else, even you, look very different than me on the protein level. So in that sense, we want to have a match as far as organs go. And you really want to match those MHC proteins especially. Those are really key for matching. But if they don't match, sometimes you have a little wiggle room. But the problem is that people receiving the organs have to be on immunosuppressants the whole time so that they don't end up, their immune system doesn't start attacking the organ. And there's also another problem where the organ, you can't get rid of all the immune T cells and all the cells that live in the blood from the organ when you transplant it. So some of those cells come along too. And so it almost has its own little immune system. And if it's strong enough, the organ can attack you. So if you were lucky enough to get a heart transplant and get a new heart, it's really important that your heart doesn't start killing you either. So that's why kind of general immunosuppression can eliminate that problem. Any questions on that? Questions? Okay. Autoimmunity, again, this is a problem. If your immune system, those T cells weren't educated correctly, there's a chance that, depending on your genetics, that those T cells can come back to haunt you and kill you, literally. And they will start attacking organs in your body or something. The one that I did some research on was type 1 diabetes, in which the T cells actually start killing your pancreas, the cells in your pancreas, and then those people aren't able to produce insulin, and therefore they can't process glucose correctly. Big problem, big problem. And it's a problem that affects kids. And so it would really kind of stink to have autoimmune disease anytime, but as a kid, it's especially hard. So, what's that?
Is it more aggressive?
It just happens earlier because there was some sort of event early on that triggered that response. And so if you even have one T cell in all the T cells in your body that recognizes your pancreas as bad, it will get stimulation that it's doing the right thing once it comes in contact with your pancreas. And when that happens, you make more and more and more and more T cells. So then most of your T cells are against your pancreas, and those are the ones that start living. And then you have really big problems because your pancreas is going to be gone by the time you need it. So, yeah, autoimmunity is another important component of the immune system. And again, immunization. Again, this is really important as far as the memory. So every time you have an immune response, some of those B cells and some of those T cells are reserved in like a special bank, you can think of it. And those cells are kind of immortal. And they live for the whole duration of your life. And they keep you from having that really bad reaction to that same pathogen the second time. So they give you some memory. Say, oh, I've seen you before around here. You're not welcome. Let's kill you right away. Okay? And also, again, immune deficiency, when all our parts of the immune system are not functioning, at this stage, the person is susceptible to infection. Yeah?
Can they give like an immunization for like say you have food allergies? Like somebody allergic to peanuts and they're like scratching for like little peanut.
That would be great, right? People are trying to do that. People are trying to make immunizations for, say, allergies or asthma or some of the non-infectious type of components. And the trick there is really finding the window of opportunity as far as when does that exposure have to happen and how much to give to get that immunity later. But the problem is that it's so much of an overreaction right now, it's almost killing too much. Whereas, say, with the smallpox example, there wasn't enough